last time at the end we were talking about in chapter 2 the elements on the periodic table and what particles are inside of an atom and where they are inside of the atom. We know about the nucleus. We know that the electrons are around the outside of the nucleus. We also know that an element is defined by the number of protons in its nucleus. So when we're looking at the symbols for elements, the symbol that defines the name of the element, such for example chromium is Cr, that is the same as saying that there are 24 protons in the atom, right? So the atomic number, which is the number of protons, is often not shown because it's redundant to show both the atomic number and the symbol. They mean the same thing. They mean there are 24 protons if you're specifically talking about chromium. However, the mass is important. The mass number, which is the sum of the protons and neutrons combined, does vary for an individual element. So not all atoms of chromium have the same mass. All atoms of chromium have the same number of protons, but they don't all have the same mass. So when you see a symbol written down and you see a whole number for the mass, meaning it's not a fraction or a decimal, then they are talking about a specific atom, one specific atom of chromium, and you can determine how many neutrons are in that atom by taking the mass, the total mass of those protons and neutrons combined, subtracting out the protons, you'll know how many neutrons there are. If you have a periodic table, however, the mass is always given as a decimal. So for chromium, it's 51.9961. Where does that number come from? Does that mean that all chromium atoms have a mass of 51.9961? No, that number is an average of the naturally occurring isotopes. So for chromium, the average mass is very close to 52. Right, so if I take 52 divided by minus the 24 protons, the mass of 52 minus 24 protons means on average chromium should have 28 neutrons. There may be some chromium atoms with more than 28. There may be some with less. So if you see a symbol written down that looks like this, and it says chromium 53 with a whole number here, this is communicating this is a specific version or isotope of chromium that has a mass of 53, which would be 29 neutrons along with the 24 protons that chromium always has. So this is a way of communicating something different. This is one specific atom or version of the atom. The mass on the periodic table is a naturally occurring average. So if I have a sample of chromium in the lab and it's a natural sample, it's going to have lots of different chromium atoms with different masses in there, but the average mass of those will be this mass on the periodic table, and that's usually what's useful if I'm working and doing calculations with a sample that has billions and billions of atoms. What I want is their average mass, I don't need to know the mass of every single one. But if I'm asking you a question about specific isotope, like for example hydrogen, if I say, I give you a symbol, and I say how many protons, neutrons, and electrons are in here, then I'm looking at a specific atom. I don't have a sample of hydrogen with a variety of isotopes that all have different numbers of neutrons. I'm looking at a specific example. So hydrogen comes in three forms. It comes in as a proton, it comes as deuterium, it comes as tritium. The protium and the deuterium, the first two, with a mass of 1 and 2 respectively, those two are naturally occurring. They are stable. Tritium also occurs naturally. It's formed through a variety of processes, but the amount of tritium in the environment is very, very small because it is not stable. Its nucleus is not stable. Having 2 neutrons with 1 proton, for some reason, the strong force that holds that nucleus together is not as strong as it should be, and that nucleus will break apart over time and undergo changes. So the amount of tritium in the environment at any given moment is usually small, unless you live next to a nuclear plant that just has a nuclear spill or something like that. But the difference between the three versions of hydrogen is not the number of protons, it's the number of neutrons. So when I look on the periodic table at hydrogen, I see a mass of 1.00794. That's the average of these three isotopes. So if I'm taking the average of a mass, the average of three things, where one has a mass of 1, one has a mass of 2, and one has a mass of 3, and I average the numbers 1, 2, and 3 together, I get an average of 2. So why isn't the mass on the periodic table 2? Why is it 1.00794?
Doesn't it have something to do with what percentage of each is in, like...
Yeah, right. It has exactly to do with the natural abundances of the different isotopes. So as we said, tritium is very rare. So even though it's there, I can't average it to find the average mass and weight that with an equal priority that I weight the other two isotopes, because it's very rare. And even deuterium is much less common than a normal proton for my hydrogen atom. Like 99% or more of hydrogen atoms don't have any neutrons. That's why the average is so close to 1, because we have to factor in their percentage abundance in nature to get that average. So if I have a sample of hydrogen in nature, the average mass will be just above 1, because these other two isotopes are not very common and they don't really contribute much to the average. So that brings us to another point about the nucleus, and that is that not all nuclei are stable. We talked about this last time. We said you need to have a number of protons and the neutrons in the nucleus that create a stable nucleus, and that will only happen if the strong force is able to overcome the repulsions between the protons, right? So we know there's the electrostatic force. That's attractions between opposite charges and repulsions between like charges. So last time we talked about in the nucleus, there are no electrons, it's just these protons and neutrons. The neutrons don't have a charge, but the protons are all positive. So if I jam a bunch of positively charged things into this atom, that's going to cause a lot of repulsion. There needs to be the right ratio of particles in there to create enough attraction to overcome that repulsion. And so if we look at the ratio between protons and neutrons, this red line here represents a 1-to-1 ratio. So most elements are not stable with a 1-to-1 ratio of protons and neutrons. The band here, these are the isotopes that actually exist and are stable. So I can't make an isotope with 60 protons and 60 neutrons. That would be here. That's not in the band of stability. If I had that isotope, that's not a stable atom. That nucleus is going to break apart in one way or another and be radioactive.
Is the line is the ideal?
No, the band. This is the band of stability, or the belt of stability. This area in the highlighted area includes the isotopes that are stable. So if you're not in that area, if you're over here, and you make an atom with those particles, it's not going to be a stable atom. Anywhere outside of this highlighted area, I could make an atom with, theoretically, I can make an atom with any number of protons and neutrons. So if I take 100 neutrons and add only 20 protons and I'm up here, that's not anywhere near the stable area. That's not going to be a stable atom. So the reason I wanted to focus on this is because there's a misconception sometimes that a stable atom has equal numbers of protons and neutrons. That's only true near the top of the periodic table until up to about 10 or 15. Once I get past 10 or 15 protons, once I'm in this area around aluminum, phosphorus, once I go beyond that, the vast majority of the elements are below that, they're not stable with an equal number of protons and neutrons. For those, you need more neutrons than protons to balance out some of that extra repulsion between the neutrons. But we'll talk a lot more about that in detail in general chemistry too. So we're not going to get into too much detail on that. The point of this was to show that each element has the option of having different numbers of neutrons, but only certain numbers will actually make a stable element, and we know that based on which elements are radioactive and which elements aren't.